So now that we know how it is supposed to work, let's look at some code. And I know in the past lectures I always basically live coded everything, but this time it's quite a lot of code, so I hope you'll forgive me for having it prepared, and I'll just walk you through it. So as always, you can find the code in our GitHub repository. So let's first look at the code, the Plutus code that implements the Oracle itself. So I put that into module week 6 Oracle core. Right, so first of all, the Oracle will be a parameterized contract. And this data type that I call Oracle is the parameter. And it will depend on 4 fields. So this is a record type with 4 fields. First, the O symbol is the currency symbol of the NFT. So the NFT that will always be carried around with the Oracle UTXO to uniquely identify it. I don't need the token name because I will just use the empty string as a token name. Second, the operator, that's the owner of the Oracle. That's the one that can make updates. We saw just now that the use operation is supposed to be used by anybody, but the update operation, where the datum actually changes, can only be done by the operator, and that public key hash here identifies the operator. Then the fee is the fees in Loveless that are due each time somebody uses the Oracle. This fourth field, OAsset, identifies the target of the Oracle basically. So in this running example, we're talking about exchange rates, ADA to something else, and this denotes the something else. So in our example, this would be an asset class representing some sort of US dollar token. So we do the usual boilerplate, the type classes we need for it to be serializable and liftable. And now we define the redeemer. And as we already saw in the diagrams, I want to support 2 operations, update and use. So I just define a new data type that I call Oracle Redeemer that just has these 2 values, update and use. And I use template Haskell to implement isData for that redeemer type. Then just some helper definitions. So as I said, I want to use the empty string as a token name for my NFT. So this is this Oracle token name. And this is just a way to identify the NFT asset class given an Oracle. So this is not to be confused. Maybe the name is not good. This Oracle asset is not to be confused with the O asset. So remember, the O asset is US dollar token in our case, whereas the Oracle asset will be the asset of the NFT that is used to uniquely identify the UTXO with the Oracle value. So it's just a simple matter of extracting the symbol from the Oracle and then using this fixed token name, which is just the empty string. The next function here, Oracle value, is a little helper function that, given a TX out and a way to turn a datum hash into a maybe datum, returns a maybe integer. So the TX out in question will be the output of the UTXO that holds the Oracle. And then we want to somehow look up the datum of that Oracle and turn it into an integer. Why integer? In the example, when I showed you the diagrams, we used rational values or real values or double values for the exchange rates, 1.75 or 1.77. There is a ratio type of rational numbers in Plutus, but that has some issues that I think it's not, it doesn't implement toJSON and fromJSON. So I felt it was easier to just use integer for the Oracle values. So basically I just take the true exchange rate and multiply it by 1 million and then round. So an exchange rate of 1.75 would correspond to the integer value 1,750,000. Right, and so we will see later how this helper function is used, but it's quite interesting example of using monadic computation in a monad that's not IO or, for example, contract. So in this case, it's the maybe monad. So this do block here, these monadic operations happen in the maybe monad. So that means the bind captures the fact that this could go wrong and we could get a nothing, in which case the overall result is nothing. So it's just 3 steps. First, we take our TX out and try to get the TX out datum, which can fail because not any output has a datum. It could be a public key output that doesn't have a datum. But if it succeeds, we get a datum hash. So that's this DH. Next, we use this provided function f, the second argument, to maybe turn this datum hash into a datum. So this can again fail, but if it succeeds, then we get a datum D. Datum is just a new type wrapper around built-in data. So then we can use Plutus TX dot from built-in data to maybe turn this D into an integer. So of course there could be a problem that the datum is there, but it's not an integer, it's some other data type, in which case this would fail. So we have to do these 3 steps and each of them can fail. And this is a nice application of the maybe monad where using this monadic computation, this monadic notation makes it much nicer to write down. And as I said, we'll see in a bit where we use this helper function. So this is now the most important function, the make oracle validator. So it gets the parameter, which was our data type oracle. Then it gets the datum, which, as I just explained, is integer in our case. Then it gets the redeemer, represented by the data type oracle redeemer. And finally the context, and returns a Boolean whether we should validate or not. And I mean, we do have 2 cases for use and for update, but there are some similarities between them, as we saw in the diagrams. Because in both cases, we want to check that we have the input that holds the NFT, and there is an output that again holds the NFT. So those 2 checks I can do for both cases simultaneously. That's why I do them up front. So this first checks that the input I'm validating holds the NFT, and that second condition checks that there is an oracle output that also holds the NFT. And then I distinguish the 2 cases that I'm in the update or the use case. So let's first look at input has token. So first, before I get to that, I have 2 more helper definitions here. So info that we saw before, I just take the context and extract the transaction info from it. And own input, this is the output that I'm just trying to consume. So validation is running, as you know, whenever I try to consume a script input. So in this case, I try to, or script output, in this case, I try to consume the oracle output. And this TX out is supposed to be that oracle output. And there is this function that's provided by the Plutus library, find own input, which given the context gives me that input. But that case is a maybe, because I might be in a situation where I'm not validating input. I might be in the monetary policy context, for example, in which case there is no input that is being validated. So this nothing case should not really happen, because we know we are validating the consumption of the oracle. But in any case, if that nothing happens, I just say there is no input, but we should never end up there. And if we have an input, then it's of type TX in or TX input. And then I can use this TX in info resolve to get the corresponding out, TX out. So this own input is now the output, the oracle output I'm trying to consume. So now I must check that the token is present. And there's in the ledger.value module, there's an asset class value of function that takes a value and an asset class and then returns an integer, how many coins of that asset class are contained in the value. So as value, I use TX out value of my own input. So that's the value attached to this input I'm consuming. And as asset class, I just use this helper function Oracle asset Oracle. So that gives me the NFT belonging to the Oracle. So I check how often is the NFT contained in the value of the Oracle output, and it should be there exactly once. I mean, because it's an NFT, it can never be more than one, but it could be missing, in which case it would be 0. So I must make sure it is actually there. So I check whether it's 1. Next helper function, own output. As we know in both cases, use and update, I want exactly one Oracle output again. So I first want to find that. There is another function defined in the libraries called get continuing outputs that gets the context, and it returns a list of all the outputs that go to the same script address that I'm presently validating. So right now we are in the context of validating the Oracle, the consummation of the Oracle output. So this get continuing outputs will give me all the outputs of the transaction that again go to the Oracle address. And I want there to be exactly one Oracle output. So if this get continuing outputs results in a list with one element, I return this one element. And if it's 0 or more outputs going to the Oracle address, I produce an error and say I expected exactly one Oracle output. Now I can use this very similar to input has token. I can now check whether output has token. So that's basically exactly the same, except that earlier the value was from the own input, and now I take the value from the own output. And again, check that this NFT, which is given by Oracle asset Oracle, is contained exactly once. So this now checks that my Oracle input carries the NFT, and this checks that my Oracle output carries the NFT. So this covers these first two lines here, which are common for both cases, for the use and for the update case. And now I make a case distinction whether I'm in the update or in the use case. So let's look at the update case first, which was the second one in the diagram. And there are two conditions we must check. We must check that the operator actually signed the transaction. This is so simple to check that I did it inline, so I didn't write a specific helper function for that. I just used this tx signed by that we have seen before. It takes the info and it takes the signature we want. And remember, we know the operator from the field in our parameter, in the Oracle parameter. So operator Oracle gives us this public key hash of the operator, and we check here that the transaction in the update case is actually signed by the operator. And the second condition we want to check is that it again carries valid data. So as you know, in the update, it can, the exchange rate in the datum can arbitrarily change, but it should still be of the right type at least. So in our case, it should still be an integer. So I check that here using first the helper function output datum, which gives me a maybe integer. And I just use this helper function we discussed earlier, Oracle value, which now takes my own output. So I'm interested in the new value, not in the old value. The old value I have given here as parameter to my validator anyway. That's the second argument, the x. So x is the old Oracle value. But now I'm interested in the new Oracle value, in the datum attached to the Oracle output. So I use my helper function Oracle value applied to this Oracle output. And remember, there was a second argument that given a datum hash gives me a datum, or tries to give me a datum. So it's a function of type datum hash to maybe datum. And there is one called find datum that takes the info. So find datum takes the info and the datum hash and then tries to look up the corresponding datum. So this has exactly the right type, and that will give me just the new Oracle value in case it succeeds, and if something goes wrong, it will give me nothing. And now to check that it's valid, I don't say anything about the value of this integer. All I care about is that it's not nothing, so it's some integer. So here in the valid output datum, I just take this output datum, which is maybe integer, and check that it's not nothing, that it's a just. And there's a function in the prelude called isJust that does just that. So isJust will be true if it's a just and will be false if it's a nothing. So this is the second condition I check here. So all I check is that the operator has signed the transaction and that, again, I have a valid integer as output datum. In particular, I don't check anything about the value apart from the fact that it must carry the NFT. So that means that this allows the operator in this transaction to retrieve the fees that have accumulated in the value. I only check that the NFT is there. I don't check that any other value that was on the input side is still there on the output side. So that allows the operator to get his fees. Now the second case is the use case, which can be used by anybody, as we saw, but it is much more restrictive because we don't allow the datum to change. So when you use the oracle, you don't change the value of the oracle. This is the first condition. We already have this helper function output datum, which is a maybe integer. That's the new value of the oracle. And I just check that it's just x. Remember, x was the old value of the oracle, so I just make sure that the datum hasn't changed. And finally, I must check that the fees have been paid. So remember, when you use the oracle, you're supposed to pay fees. So this is a final helper function here. So I just look up the value that was attached to the oracle input using txout value of our own input. I check the value that's attached to the own output. And now I know that the output should be at least as large as the input plus the fees. So this is exactly what this says. Output value should be greater or equal than the input value plus, remember, we can use the semigroup operation to combine values, plus, and this is the fees. So remember, the O fee field in the oracle parameter was just an integer, and I said that's the fee in Loveless. So I used the ada.loveless value of function to turn this integer into a Loveless value, add it to the existing input value, and then I say that the out value should be greater or equal than this. I could, of course, also have said equal. That would also be correct. By writing greater than equal, I basically allow users of the oracle to give the operator a tip. If they are very happy with the oracle, they can give more than just a fee. They can pay more. I mean, that's just a matter of taste. I could have written equal. And remember, also recall that, I mean, in the example on the input side, there was just the NFT in the value, and on the output side, there was the NFT and one ADA fee. And then in the next step, there was an update, so the operator collected that fee immediately. But this is now designed in a way that the operator doesn't have to collect all the time. So there can be several uses where fees accumulate over time. And then with the next update, the operator can collect all of them in one go. Okay, this is basically the core business logic of the oracle. This is now in code what I tried to explain earlier when I showed the diagrams. And now it's just the usual boilerplate. So I have this helper type oracling where I just combine the redeemer and the datum type. So I say the datum type is integer, the redeemer type is oracle redeemer. Then I do the usual template Haskell stuff to compile it to typed validator. And because it's parameterized, I do what we always do with parameterized. So I have to use this apply code and lift the parameter into Pluto script. So now we have the typed validator, and then we can use the usual boilerplate here to turn it into a validator and to turn the validator into an address. So now we have our script oracle address. And that concludes the on-chain part of the oracle code. Now I also provide some off-chain part, namely to actually start an oracle and to update it. Not to use it, because how it is used exactly depends on who wants to use it, in which context. So on the diagram, we had the swap example, but there can be many other examples. I called it an open API earlier. So to create a valid transaction that actually makes use of the update, of the use redeemer is not the responsibility of the author of this Oracle contract. Whoever wants to use the Oracle will make sure to create a transaction that actually invokes this. So this is the first time we see something like that, where we have some on-chain code that is basically not mirrored or reflected in the off-chain code. So here we only do what is the responsible of the Oracle provider. Right, so as I said, two operations: start the Oracle and update it. And to start it, we need parameters, the fees that we want to charge, the currency symbol and the token name. This is now the currency symbol and the token name of the asset we want to track. So US dollar token in our case, not the NFT. Because at this point, we don't know the NFT yet. We will actually mint the NFT in this start Oracle contract function. And that's actually all we will do. So we won't provide an initial value for the Oracle yet. All we want to do in the start Oracle function is mint the NFT. The reason for that is that this minting of the NFT can take a couple of slots. So if we already provided the initial data for the exchange rate, that might be outdated by the time we are ready. So therefore I decided to not do that here. So that will be handled in the update Oracle function. So all this does is mint an NFT. And I could of course have used the code we developed in the last lecture, our NFT code. That would have been perfectly fine. But I decided to instead use one of the provided use cases from the Plutus minus use minus cases package in the Plutus repository. And there's a currency module that provides a mint contract function, and that can be used to mint NFTs. Actually, it's more general. If we check in the REPL for the type of mint contract, we see it takes a pub key hash. That is the pub key hash of the entity that will end up with the minted coins. So we will just use our own, the wallet's own pub key hash there. And then we see it takes a list of pairs of token names and integers. So this mint contract will create a currency symbol, which will depend on a unique UTXO, the same trick we used in the last lecture. But it allows you to specify not just one token name and then make an NFT with that, but several token names with arbitrary integer amounts. So you can mint several coins with different token names and also different amounts. But they all will have the same currency symbol, and it will be guaranteed that there can only be one such minting transaction. There is one slight problem if we want to use this, and that is the error type. We want a contract where we use text error messages. But this contract here is polymorphic in the error type, provided the error type implements this as currency error class. And unfortunately, text doesn't. So we can't use text here for E. So we can't specialize this function for text. That means we can't directly use it in our contract, because then we would get an error that text doesn't implement as currency error. Luckily, there's a function called map error. Let's look at this. So that has this signature, and this allows us to change a contract with error type E into a contract of error type E prime, provided I can turn E into an E prime. So if I can turn error messages of the one type into error messages of the other type, then I can turn a contract using the first type of error messages into a contract using the second type of error messages. So that's what I'm using. And actually one type that's provided in the currency module is called currency error. So we see this actually implements currency error. So this class that we need. So this is a type we can actually use. And it also implements show. So by first using show to turn a currency error into a string, and then using pack from data.text, which turns a string into a text, we can turn a currency error into a text. And then using map error with this combination of pack and show, we can turn a contract that has currency error messages into a contract that has text error messages, which is what we need. So that's what I'm doing here. So I use map error pack after show, and then use this mint contract function from the currency module. And as list of tokens, I don't want several tokens with weird amounts. I just want an NFT. So I just have one pair in this list. Oracle token name, recall that's just the empty string with amount 1. So this will just mint me an NFT. I have to specify the type here because otherwise the compiler wouldn't know which type to apply show to. So I have to specify that I'm specializing this mint contract to currency error. And then I use map error to turn that with show and pack into a text. So now this has the right type. I can use that here. And I get this weird one-shot currency. And that is a specific type specific to the currency module. But I don't really care what that is. All I care about is that there is a function in that same module called currency symbol that takes such a one-shot currency and gives me a currency symbol. And all I need is the currency symbol of the NFT that I just minted. Once I have that, I can fill in my Oracle type. So the only information that was missing was this currency symbol. So this is now here. As operator, I take myself, my own public key hash, which I looked up here in the first line. And the fees I just take from the parameters, and the asset class I also take from the parameters. I suppose I could have used asset class here as well. Instead of having two fields, symbol and token, I could just have had one field of type asset class. But that doesn't play so nicely with the UI. And if you want to try the playground, I felt it was easier to use these two separate fields and then combine them like so. So this now gives us our Oracle, and we have minted the NFT. And I just log a message and return the Oracle. So the return type here of this function is of type Oracle. Okay, and the second function is more complicated, is the update Oracle. And this has to deal with two cases. The case that we already have an Oracle value that we want to update, that's like in the diagrams. And also the case that we just started the Oracle and there is no UTXO yet. So we want to create one for the very first time. Anyway, so it takes as parameters the Oracle, some Oracle, the Oracle parameter, and integer is the new value. So the value, the Oracle value we want to update the Oracle to. So first we use this helper function find Oracle, which is defined here. So that takes an Oracle and it's supposed to look up the existing Oracle UTXO. This can fail because the Oracle might not be there. So if we have just started it, remember we just minted the NFT. We didn't create an output at the Oracle address yet. So in that case, we won't find it. But if we find it, it will return a just, and then the triple is the TXOUTREF, which if you recall from last time, is basically the identifier of an UTXO. Then the TXOUTX, that's the UTXO itself, containing all the data. And the integer is the current exchange rate. This is, of course, encoded here in this TXOUTX, but to make it easier to work with, we extract that here in this helper function. And how do we do that? So first we use UTXO add that we already know to get all the UTXOs sitting at the Oracle address. So this is now a map from TXOUTREFs to TXOUTXs, all the UTXOs sitting at this address. But remember, if we find more than one, then most of them will be wrong. I mean, we want the one that contains the NFT. So we filter this map. This map.filter comes from the data.map module, the standard container library in Haskell, and it takes a function of type the values in the map to bool, and it will only keep those entries in the map for which this function returns true. And here we now want to check that the NFT is there. So given such an UTXO, we do similar to what we did during validation. So we check the value of that UTXO, and check how often our NFT is contained in it. And it must be there exactly once. So we will end up with a map that has either 0 elements if the Oracle UTXO is not there yet, or 1. Can't be more than 1 because this NFT can only be there once. Right, and now we distinguish the two cases. So the good case is that we find exactly 1 element. So we convert the map into a list of pairs, of key value pairs with the standard map to list function. And there are 2 cases that we find exactly 1 element or not. Actually, the second case can only be that we don't find anything. As I said before, we can't find more than 1 because it's an NFT, but Haskell of course doesn't know that. So to keep the compiler happy, I don't say just empty list here, I just use the underscore, so all other cases. Anyway, so if we find exactly 1 key value pair, then in order to return this triple, so we now have the TX-out ref and the TX-out, now we need this integer. And that could still go wrong. So even though we have the UTXO with the NFT, there could be some corrupt data in it for whatever reason. So now I use this helper function again that I explained right in the beginning that we also used in validation that gets the TX-out, which I can get from my TX-out TX by using TX-out TX-out. And remember, the second argument was a function that given a datum hash gives me the corresponding datum if it can. And the way we can do this here in off-chain code is we use the TX data field of the TX-out TX TXO. So the TX-out TX TXO gives us the transaction, and that has a TX data field, and the TX data field is just a map from datum hashes to datums. So we can use map lookup to look up a given hash, and we can find it or not. If not, it returns nothing. If we find it, it returns the value, the datum. So using this helper function now, if that succeeds, x will be the actual datum, which is an integer in our case, as we know. So in this case, we return this triple. Now we just found out the x. If this goes wrong, then it will be nothing. And if we don't find the UTXO at all, it will also be nothing. So this is find Oracle. So we try to find it. And this is just a helper definition because I need that in both cases, this constraint. Maybe we can come back to that in a second. So logically, so after we have tried to find the UTXO, there are 2 cases that we found it or not. If we didn't find it, we just started the Oracle but haven't provided an initial value yet. So this is the first case. And in this case, all we have to do is we must create a transaction that produces this output, the first output at the Oracle address. So, and this is, we only need 1 constraint, and that is the C. And I extracted that into this, into its own line because I need the same constraint later in the second case here as well. So I didn't want to duplicate my work. So I use constraints must pay to the script. So that, as the name suggests, provides a way to say the transaction I'm constructing must have an output that pays to a script address. And the arguments are the datum, the value I want to attach to that output, and that's it. Because which script is then specified here in the second argument of submit TX constraints. So the script means the script I'm looking at right now. So all these functions, these constraints functions always have like 1 script in focus. So in our case, it's the Oracle script. There's also a variant that's called must pay to other script, in which case I could pay to an arbitrary other script. And actually we use that down here, so I can talk about that there. So anyway, so the datum is x because this was one of the parameters, the value we want to set the UTXO to, the Oracle, and the datum, and the value is we want to attach our NFT. So added class value, the asset class of our NFT, and 1. So we want to attach the NFT. So this is all we have to do in that case, that the UTXO isn't there yet. So we just submit, wait for confirmation, and log a message that we set the initial Oracle value to X. Now in the other case, so we already have an Oracle UTXO. We don't care about the old datum because we want to update it anyway. So I can just use an underscore here. So now it's a bit more complicated. So now, because now I need two conditions. Again, the C, it's the same as before. So I want to create an output at the Oracle address with the new value, the value X. But now I need the additional constraint that I also must consume the existing UTXO. And this is this constraint here. So must spend script output is basically the opposite of must pay to the script. So must pay to the script creates an output, and must spend script output creates an input to the script address. And as parameters, it takes the reference to the output, the UTXO we want to consume. That's what we called oref here, that we looked up earlier. And it takes the redeemer. And in this case, it's an update, not a use, and we just have to convert it to data first and then to a redeemer. And in order for this to work, we need to provide a couple of lookups. So first of all, in order to find this output that it wants to spend, we must use the unspent outputs lookup, which gets a map of the UTXOs that we want to consume. In this case, we can use map singleton to construct this map, which will create a map that contains exactly one key value pair. So map singleton takes the key and the value as arguments and creates a map with one key value pair. So we just put this one UTXO oref-O into this map because there's nothing else we want to consume. So all we need is this. And then we must provide the script instances. And basically, we have to do it twice, once for the input side and one for the output side. Because, so we give the Oracle instance in the lookups, and we give the Oracle validator in the lookups. And I always forget which we need for what, but anyway, so one is for to be able to consume the input, and the other one is to be able to pay to the output. And we didn't need that here because in the first case, because we provided the instance here in the submit tx constraints function. But now we have to use submit tx constraints with, because we have lookups, and that doesn't have this parameter where we can provide the instance. So therefore we have to provide the instance in the lookups itself. So it's a bit confusing, but you get used to it, I hope. And we also have to give the compiler a nudge here to tell it what script we are talking about. Remember, I said all these constraint functions are always specific to a particular script. And this basically signals what type, datum type, redeemer type this script has. So that was this weird oracling type I defined earlier, this helper type that just says datum type is integer, redeemer type is Oracle redeemer. And we give the lookups and these constraints, and then hopefully get a balanced transaction that we submit, and we wait for confirmation, and we log that we updated the Oracle value to X. So again, the logic of update Oracle is first we check whether the Oracle is already in existence. If it's not, we create a transaction that simply creates the first UTXO with the Oracle value. So the Oracle value is the datum, and we attach the NFT. And if it already exists, we create a transaction that consumes the existing one and creates a new one with the updated datum, and again containing the NFT. And note that I said something about fee collection earlier, and this will happen automatically here. So the way this balancing works. So say that this UTXO, the existing one, already contains fees, not just the NFT. So in the constraints, we just say that we want to consume the existing one, and we want to provide a new one that contains the NFT. So if the existing one already contains fees, and we say that in the new one we only want the NFT, then we have an imbalance, right? On the input side we have the fees, and on the output side we haven't specified anything about that. And then what this balancing algorithm by default always does is it pays that to our own wallet. So if there's such an imbalance, so if this already contains fees, then it will automatically here in this line when it constructs the actual transaction, create an output that goes to our wallet and can trace the difference, so the fees. And also it will automatically create an input to pay the transaction fees with. So even though we only specify two things here, the Oracle script input and the Oracle script output, we might end up, or we will probably end up with a transaction with two inputs and two outputs. One additional input coming from our wallet to pay the transaction fees, and one additional output going to our wallet, giving us the Oracle fees that users of the Oracle added to this UTXO. And I think that's basically it. Okay, then, so this is basically the bare bones that you need. Now I also, for later, provided a function that combines this into these two operations into one contract. So this is then for use, for example, in the playground or in the emulator trace monad, or also, as we will see, in the PAB. So I define Oracle schema, which just contains one endpoint, the update integer endpoint. So all that does it takes the new value as parameter. And what does this run Oracle do? So first it uses our start Oracle function to actually start the Oracle, which, remember, doesn't do anything Oracle-wise, it just mints the NFT and gives us these Oracle parameters. Then, for reasons that will become clear later, I use tell to write the Oracle value, so this parameter. And this is the reason is I need to communicate this parameter value to the outside world so that people can use my Oracle. So at time of writing, I don't yet know what currency symbol this NFT will use, so I don't know the value of this Oracle parameter yet. So I will only find that out at runtime, so once the Oracle is actually started. And then other people that want to use my Oracle need to know this parameter in order to parameterize their contracts correctly. So I have to communicate that out. And the way to pass information out of a contract is by using tell. Now this last and just, remember the tell expects monoid type. So a typical use from the writer monad is lists, like list of strings. That's when we talked about monads. I used that as an example. So each tell will take a list of strings, and then they will all be concatenated to one big list of all log messages. But it doesn't have to be lists. It can be other monoids. And in data.monoid, we have this last monoid. So I must import that from data.monoid. If we look for information, it's just a new type wrapper around maybe. And the point of it is to change or provide a specific monoid instance. And the idea is, as the name suggests, it's the monoid operation that always remembers the last value. So let's say I have last just x and combine that with last just y. Then I get last just y. So it forgets about the x and remembers the y. But if the second one is a nothing, it will remember the first one. So basically what the last monoid does, it always remembers the last just value. If both are nothing, it will be nothing. Okay, now it complains because it doesn't know whether it's nothing int or character. It assumes it's nothing unit. But anyway, so it's nothing. So last nothing and last nothing is nothing. But if one of the two is a just, it will remember the last just. And this is very useful, and it's used all the time in these contracts for the tell, because it basically allows us to keep a current state. So it will the value of the log will basically be the last just we told. And actually in this contract we will only do that once. So after starting the Oracle, so in the beginning it will end up as nothing, last nothing. So at the beginning it will be last nothing, and then we mint the NFT, we get our, in line 192, we get our Oracle value, and then we tell it. And from that point onward, it will always have that value. So as soon as we have our NFT and have our Oracle value, if other contracts from the outside query the state, they will always get the just Oracle. So they will be able to discover the value of Oracle. Okay, and then, so after I've started it, I just call this helper function go with Oracle as parameter, and this will now loop forever. And all it does is it will block at this update endpoint. And as soon as somebody provides an integer, which is the new value, it will call our update Oracle function with this value and then just loop to go again. So what this run Oracle does is it starts the Oracle, tells the Oracle so that others can discover it, and then forever just waits for new values and updates the Oracle accordingly. So that's the run Oracle function. And that concludes the code for the Oracle itself. So that's the core Oracle code, both on-chain and off-chain. So what's now missing is an example, some contract that actually uses the Oracle, a swap contract. And then, of course, using the Plutus application backend to actually run this code in the real world, or at least in our case, in a simulated blockchain.